The Roman concrete mystery, how they built structures that lasted millennia. Intro. Imagine massive, awe-inspiring structures built to millennia ago, standing today as testaments to an empire's might. The Pantheon's colossal dome, still the largest unreinforced concrete dome in the world. Harbors, piers, and breakwaters that continue to withstand the relentless assault of the sea. These aren't just ruins. They are engineering miracles, built by the ancient Romans with a material so revolutionary, its secrets were lost for over 1,000 years. Modern concrete, the foundation of our cities, typically crumbles within a century. Roman concrete, however, only seems to grow stronger with time, defying the elements and the ravages of millennia. What was their secret? Did they possess a lost, ancient technology? A forgotten formula that allowed them to build structures of unparalleled durability? Join AdventureHidden as we journey into the heart of the Roman Empire, explore their incredible architectural feats, and unravel the enduring, the mystery of Roman concrete, a material that literally stood the test of time. Chapter 1. The Foundations of an Empire. Roman Engineering Prowess. The Roman Empire was not just built on military conquest, but on a foundation of unparalleled engineering innovation. Concrete was at its heart. An empire of builders. From bustling cities to far-flung outposts, the Romans were master builders. Their extensive network of roads, aqueducts, bridges, and monumental buildings connected and sustained their vast empire. This was made possible by their ingenious application of engineering principles and, crucially, their groundbreaking use of concrete, revolutionizing architecture before concrete. Grand structures were primarily built from cut stone like the Greeks or brick. These methods were laborious, expensive, and limited in form. Roman concrete, Latin opus cementitium, offered unprecedented flexibility and strength, speed and efficiency. It allowed for faster construction than traditional stone masonry. Versatility of form. Concrete could be poured into molds, enabling the creation of complex shapes, vast arches, and monumental domes that were previously impossible or prohibitively difficult with cut. Stone. Cost-effectiveness. Using readily available local aggregates, concrete was often more economical than transporting vast quantities of cut stone. Iconic examples. The legacy of Roman concrete is visible across the empire. The Pantheon c. 126 AD, its massive, unreinforced concrete dome 43.3 meters or 142 feet in diameter, stands as the ultimate testament to its strength and the Romans' architectural daring. Colosseum c. 80 AD. While faced with stone, its core structure relied heavily on concrete. For its intricate network of vaults and foundations. Aqueducts. Many Roman aqueducts utilized concrete cores, faced with stone or brick, ensuring their durability for transporting water across vast distances. Baths of Carpacallus c. 216 AD. Immense concrete vaults spanned vast spaces, showcasing the material's capacity for creating grand open interiors. These structures weren't just functional, they were statements of power and permanence, a direct reflection of the material that allowed them to endure. Chapter 2. The secret ingredient, volcanic ash and lime. For centuries, the precise composition of Roman concrete was a puzzle. Modern scientific research has finally begun to unlock the secrets, pointing to a key ingredient from the earth itself, the basic components like modern concrete. Roman concrete consisted of aggregates like gravel and broken stone and a binder. Romans used various aggregates depending on local availability, including crushed rock, brick, and even volcanic tuff. Binder. The binder was the crucial difference. Instead of modern Portland cement, the Romans used a mixture of lime, calcium oxide, and critically, pozzolana. The pozzolanic power. What is pozzolanic? Pozzolana is a fine, siliceous, silica-rich volcanic ash found in abundance in areas like Pozzi near Naples, hence the name. The chemical reaction. When mixed with lime and water, pozzolana doesn't just dry, it undergoes a pozzolanic reaction. The silica and alumina in the ash react with the calcium hydroxide from the slaked lime, forming additional calcium silicate hydrates, CSH, and calcium aluminate silicate hydrates, CSH compounds. These are the same compounds that give modern Portland cement its strength, but the Roman version forms them in a more complex and durable way. Unrivaled durability. This reaction creates an incredibly dense, strong, and highly resistant material, particularly effective against chemical degradation, especially from saltwater. Seawater superpower. For structures exposed to seawater like harbors and breakwaters, the Romans often used volcanic ash from specific regions such as Baiae, which contained unique mineral compositions. When this particular ash was combined with lime and seawater, it formed specialized, very durable, aluminate calcium silicate hydrate CRS minerals, including a rare mineral called philipsite and the more common tobamorite and tobamortite. These minerals grew over time, filling microcracks and making the concrete essentially self-healing and stronger in corrosive environments. This was a critical lost aspect of their technology that modern science is now rediscovering. unique combination of volcanic ash, lime, and often seawater allowed Roman concrete to achieve a longevity that baffles modern engineers using seemingly superior materials. Chapter 3. Self-healing and ever-strengthening the Pantheon's secret beyond its initial strength. Recent research suggests Roman concrete possessed a remarkable ability. It could self-heal and continue to strengthen over millennia. The Pantheon's enduring dome. The Pantheon's dome is a prime example. For nearly 2,000 years, it has stood without reinforcement, defying gravity and weathering. Its secret lies not just in the ingredients, but how those ingredients evolve over time. Lime clasts and hot mixing. In 2023, a study published in Science Advances revealed another crucial aspect: the presence of small white chunks of lime known as lime clasts within the concrete, which were previously thought to be simply unmixed lime. Hot mixing. Researchers now believe these lime clasts were intentionally used, and the Romans likely mixed their concrete at very high temperatures. Hot mixing. This process created a more reactive material, self-healing mechanism. When microcracks formed in the concrete due to stress or environmental factors, water would seep in. This water would react with the highly reactive lime clasts, forming a calcium-rich solution that would then recrystallize and fill the cracks, effectively healing the concrete from within. This is known as autogenous healing, continuous hydration and mineral growth. Unlike modern concrete, which largely stops reacting after initial curing, the Roman mix, particularly the seawater concrete with volcanic ash, undergoes long-term reactions. Minerals like tobermorite and philipsite continue to grow and crystallize within the matrix, interlocking over time. This process effectively makes the concrete denser and stronger with age, especially when exposed to water. A living material. This understanding transforms Roman concrete from a merely robust material into a living one, capable of dynamic chemical reactions that enhance its properties over millennia. This level of sophisticated long-term material science was utterly revolutionary for its time and represents a significant lost ancient technology that modern engineers are now eager to replicate. Chapter 4. The decline and rediscovery, a lost art despite its incredible properties. The secrets of Roman concrete largely faded after the fall of the Western Roman Empire. Loss of knowledge as the Roman Empire declined and eventually fragmented in the 5th century. Much of its advanced engineering and architectural knowledge was lost. Disruption of trade and infrastructure. The complex supply chains for materials like specific volcanic ashes and the centralized organization required for large-scale concrete production collapsed. Shift in building practices. Medieval Europe saw a return to simpler construction methods using local stone and timber, with a focus on cathedrals and castles built by skilled masons, rather than the vast concrete structures of Rome. Lack of written records. While some Roman architectural treatises exist like Vitruvius's De Architectura, they often lacked the detailed recipe or scientific explanation for concrete's extraordinary durability, relying more on practical instruction. The subtle nuances of hot mixing and specific pozzolana use were likely tacit knowledge, passed down through generations of skilled craftsmen, not fully codified. The Dark Ages for concrete. For over 1,000 years, the ability to create concrete of Roman quality was effectively lost. Medieval builders constructed impressive structures, but nothing on the scale or durability of the Pantheon without immense buttressing or reliance on pure stone. Rediscovery in the modern era. 18th century onwards, interest in concrete revived. During the Industrial Revolution, engineers experimented with hydraulic cements. Portland cement. 19th century. The invention of Portland cement in the 19th century by Joseph Aspin was a breakthrough, leading to the modern concrete industry. However, even this modern marvel does not match the long-term durability of its Roman predecessor, particularly in harsh environments. 21st century research. It wasn't until the late 20th and early 21st centuries, with advancements in material science, electron microscopy, and chemical analysis, that scientists could finally deconstruct Roman concrete at a molecular level and truly begin to understand its extraordinary secrets. This ongoing research is not merely academic, it holds profound implications for the future of sustainable and resilient construction. Chapter 5. Lessons for the future sustainable and resilient concrete. The mysteries of Roman concrete are not just historical curiosities, they offer invaluable lessons for modern construction, particularly in the face of climate change and the need for sustainable infrastructure. Modern concretes. Limitations. Durability. Modern Portland cement-based concrete often degrades faster, especially in saltwater environments, due to chemical reactions that lead to cracking and spalling. Environmental Impact: Portland cement production is energy intensive and a significant contributor to global carbon dioxide emissions, around 8% of global CO2. Replicating Roman resilience. Understanding Roman concrete's self-healing properties and its long-term mineral growth offers exciting possibilities. Self-healing concrete. Researchers are actively working on bioconcrete or self-healing concrete that incorporates bacteria or encapsulated healing agents to repair cracks. Mirroring the Roman method. Sustainable alternatives. The Roman reliance on pozzolana, a natural, often waste product, rather than solely energy-intensive clinker production, could inspire new, greener cement recipes using volcanic ash, fly ash from coal combustion, or other industrial byproducts. Extreme environments. Replicating the Roman formula for seawater concrete could revolutionize marine construction, building structures that thrive in the ocean rather than corroding. Imagine seawalls, offshore wind farms, or floating cities built with materials that grow stronger over centuries. The legacy continues. The Roman concrete mystery, once a frustrating enigma, has become a beacon of inspiration. It reminds us that ancient technologies, seemingly primitive by today's standards, sometimes contain sophisticated wisdom that we are only now beginning to fully appreciate and rediscover. From the enduring arches of the Colosseum to the vastness of the Pantheon's dome, Roman concrete whispers lessons across millennia, urging us to look to the past for solutions to the challenges of our future. This lost ancient technology is now driving a new era of innovation in construction. Outro: from the monumental arches spanning ancient rivers to the impossible dome of the Pantheon, Roman concrete stands as a silent, enduring marvel. For nearly two millennia, its secrets lay buried, dismissed as mere historical footnote, only for modern science to reveal a lost ancient technology of unparalleled genius. The Romans didn't just build structures, they built a legacy of resilience, crafting a material that defied the very concept of decay, a material that literally grew stronger through the ages. The mystery of their living concrete is more than an archaeological puzzle. It's a profound lesson in material science, sustainability, and the boundless ingenuity of humanity as we strive to build our future. The enduring strength of the Roman Empire's foundations offers a timeless blueprint for structures that truly lasts millennia. This has been Adventure Hidden, and we hope you continue to explore the mysteries that blur the lines of history and